Thank you. Let's see if I can find what I'm looking for here. So are you able to see this screen
Yep.
there? It says
Yep.
hyperon, so forth.
Yep.
Okay.
We do see the first slide.
Good. Well, that gets us going. Okay. Well, thank you, Gregory, for inviting me today. I'll be teaching almost immediately after I'm done speaking, so I'm sorry about that. I'd have to jump away so fast, but this has really been great and fantastic talk, Peter. Quite an act to follow. Anyway, I do want to talk about hyperon polarization, and I want to stay with just a focus on two simple cases, which I think are really quite interesting. And as I was thinking about this meeting and thinking about who might be around and so forth, I naturally started thinking about Nika and lower energies, and it brought me back to an interesting situation that should be applicable at high energies. And I think there's something to discover in both cases in terms of polarization. And hopefully I make that case clear. So I do want to motivate. I looked through the schedule, and I think it's worthwhile to motivate hyperon polarization as a probe of the dynamic substructure of the QGP. This is still a relatively new tool, even if it's been hotly discussed in the last 4 years. I'll talk about the low energy frontier in terms of where we're going with this sort of thing. Nika Fair, and also the RIC fixed target program, which we go down to 3 GeV root S. We have papers coming out there from this. And also the forward frontier, where here I'm talking about Nika and Fair and LHC, not so much RIC anymore, at least until, or unless there would be a tracking upgrade. Okay. So at least in the way we think about heavy ion physics, you can have perturbations on a theme and try to learn by looking at phenomena relative to a baseline. But our baseline is viscous relativistic hydrodynamics. The idea there being, of course, that we'll have a large set of equations. This is actually only a few, which involve transport coefficients, such as viscosity and so forth, that we basically are looking at conservation laws, conservation in energy momentum, and conservation of currents, if I'm looking at baryon number or even charge in principle strangeness. And that would be relevant in different parts of the phase diagram here on the left. And in fact, the phases of matter as expressed in the equation of state also feed into these equations, so that I'll have a dynamic picture as a function of space and time, given some initial condition when there's a collision about to happen. And I can calculate in principle, unambiguously, what's going to happen. And that's our standard picture of heavy ion collisions, is conservation laws, equilibrium, local equilibrium anyway, and then evolution. And when we compare to experiment, well, we'll take some region of the plasma of the fluid, it is hydrodynamics after all, and we'll blow up this little black square here, and we're taking a look at a fluid cell. Microscopic fluid cell, I suppose. It has some momentum, it has some overall velocity, it has some energy density, it might have some chemical potential associated with baryon number or associated with charm and so forth. And the hadrons that come out from that, the hadrons that we measure, reflect those properties. So if the baryon number of this little cell is very large, I'm very likely to get protons instead of antiprotons coming out. Okay? And the prescription by which we extract particles, their yields and also their momentum distribution, is dictated by this so-called Cooper-Frye formula, which is much maligned, but nevertheless, it's probably the best we have. So it's sort of a thermal connection between the fluid itself and the particles that we measure. And Peter just went through some beautiful example, and I knew that he would, so I just am showing a very old version of a plot that he showed a much better one now with X orders of magnitude. The idea being here, I said that the emitted hadrons reflect the properties of the cell, and in particular, if I'm looking at yields, I'm mostly dictated by the chemical potential, baryochemical potential, if there's a strangeness chemical potential, isospin chemical potential, at least in principle. And we see that this equilibrium model, and one can get more and more sophisticated as you treat it by using S matrix and so forth. But this equilibrium model describes the data extremely well. Okay, this is what Peter just showed. One can go on and get in a little bit more detail than just yields themselves. This then would be the momentum distribution. This is what's shown down at the bottom from Rick. This is just the DN data probably of charged particles, yes, over about 10 units of pseudo rapidity. And it's very well described by hydrodynamics. Not really surprisingly. In fact, the parameters of hydrodynamics are tuned in order to reproduce the data. And that's the way we learn about things in the quark, flow, and plasma, after all. But it's easy to understand the longitudinal dynamics with our standard model hydro. We can also understand relatively straightforwardly the transverse dynamics, the momentum in the transverse direction. And here I'm just showing the most common particles, pions, kaons, and protons and antiprotons. These are all straightforward measurements, very easy to reproduce, even the details if you worry about resonance and so forth, by our standard model. If they're easy to reproduce, they're also relatively insensitive to the critical parameters. One thing that is a little bit more sensitive to critical parameters is something that probes the momentum distribution in more fine detail. On the right here, I'm showing the PT distribution, which is basically an integral over the transverse direction. What I'm showing here on the left are the V sub n, the V2, V3, V4. These are the anisotropic yields in the transverse plane. So if I take a look at this second blob exploding, it's the shape and the fluctuations of that shape. That's much more sensitive to important parameters like viscosity, for example. And that's where you really start getting into, do we really understand the fluid in detail? And with these calculations, the answer, yes, indeed. The question is, all right, this looks fine, and almost all of the discussion and focus, at least at the highest energies, you could have looked at right down the beam pipe, as one of those movies, in fact, was doing, and not really worrying about the fact that these collisions, besides having energy and momentum and so forth, have a lot of angular momentum. It was almost irrelevant, except for an occasional nod to directed flow. Well, what happens with that angular momentum? Well, if I take a look in detail at the fluid, that angular momentum, just due to the shear dynamics of the collision, leads to a vorticity in principle at all points in the system. Excuse me. So I would have some kind of curl of the flow field, at least non-relativistically, that would be the vorticity. And those little curling elements themselves are flowing. Okay, so that curl, that vorticity, characterizes a fluid cell. So if I would come over to the right and say, okay, this little fluid cell, apparently it has chemical potential and everything else, and some kind of vorticity, how does that reflect itself in the emitted particles? How am I going to measure that? And the answer is, not surprisingly, this little bit of angular momentum shows up as the spin of the particles coming out, the polarization of the particles, of the ensemble of particles coming out of that fluid cell. Okay, so then I'm showing sort of on the left schematically, really, the probability to have a particle with a given energy, E, with a given baryon number, B, a given charge, Q, and then one can go to other charges, and a given S vector, the direction of S. S is dictated by chemical potentials. Well, I have temperature here, baryochemical potential, charge chemical potential, and now the spin chemical potential is that vorticity. It's a dynamic chemical potential. Okay, so basically we've extended the equilibrium freeze out to the spin degrees of freedom. Not obvious that that has to work. Different degrees of freedom can thermalize at different rates, but it's nevertheless what we try. And it works relatively well, I'll show you, and people are then challenging this and seeing how far you can push it. This actually connection between a fluid vorticity and a particle polarization was only first observed a couple of years ago. So it was first observed at RIC in 2016, and it was first published in any other field in 2016. This is the spin hydrodynamic generation. The idea here being that I have some fluid flowing down a channel, I think it was mercury or so. And basically just by friction of the fluid running past the walls, you pick up a vortical field. Right next to the wall, you'll have some kind of shear flow, just like a heavy ion collision, as a matter of fact. So I'll pick up some vorticity to the field, and this does get transferred to the particles that make up the fluid. That's the analogy, the perfect analogy to the heavy ion collision. And in fact, in this paper, if you look at the mathematics that follows it, he's in fact doing the equivalent of a Cooper-Frye. He finds that the probability to have a electron with a given spin direction is given by e to the minus omega dot s, just like what we see at RHIC. Of course, it's a little bit easier than what we do at RHIC. The direction of the alignment is pretty clear. It's going to be perpendicular to the surface of the water. Measuring the alignment itself via magnetic dipole moments of the electrons was straightforward. So this connection could be proven in an easy way. For us, it's a little less easy in heavy ion physics. Instead of using electrons, we're using the parity violating decay of lambda hyperon. So a lambda decays into a proton and a pion, of course, and the topology with which it decays reveals its spin. So if it's spinning along this yellow arrow, the proton in the lambda frame tends to come out along the yellow arrow. That's the idea. So we can get an estimate of what the polarization direction is. And we now also have some kind of estimate of which way the total angular momentum points. Remember, Takahashi had the surface of the liquid. We have the total angular momentum of the heavy ion collision. And we measure this by looking at forward and backward detectors. Maybe I will come here. Here's my collision. I was forced by one of my collaborators to point out that our detectors are larger than a heavy ion collision. Here's our collision, and we can tell by looking at it what direction the angular momentum points. In this case, it points right towards us. And by looking at the deflection of these spectators that move forward, I can get an estimate of that. And this is just an example. This is kind of for people who work in the field of how we quantify that estimate. And one point I want to make is when you're doing these measurements, which are rather statistically challenging sometimes, doubling your event plane resolution quadruples your sensitivity. So you can cut your runtime by 4. Okay, very good. This was measured, as I said, it was seen in with spintronics in 2016. This was published in 2017 from heavy ion collisions. This is the polarization on the y-axis. This tells us that a few % polarization is seen among the lambda hyperons that are emitted. And that's as a function of collision energy on a log scale. So the LHC is up here, and the lowest RHIC energies are down here at the left. First of all, we see a significant polarization, even if statistical error bars are large. But, you know, also very important, the data agrees very well with, quantitatively, with predictions of hydrodynamics, predictions. There had not been a polarization measurement done before. This was the first one, so no model was tuned or something like this. And yet calculations were done to predict this never before seen phenomenon, and it came out quantitatively online. That's important. Furthermore, even things that aren't strictly three-dimensional viscous hydrodynamics do well as well. For example, the three fluid hydrodynamics, which is especially important as we get to low energies, as I'll talk about. Also transport calculations, where really there you are talking about particles, but you can coarse grain it and figure out what the vorticity is in a given cell and so forth. And you as well can reproduce the data relatively well. So this is important. I mean, here we have something brand new, and it seems that at base level, we understand the phenomena. That's what I put up at the top. It's a well understood, it even seems to be calibrated tool that we can access this fine substructure. Because we really are probing the gradients of the flow field at the subhadronic scale. It's more than just, you know, V2. So it's seems to be to first order well understood and calibrated. On the other hand, there's a lot going on. One of the biggest questions in the field is shown up here at the top. I talked about the polarization along the total angular momentum direction. Obviously, that's perpendicular to the beam. There's also a polarization along the beam, and it was predicted. And it was predicted to show a quadrupole oscillation, oscillating as cosine 2 phi. And it was observed this way with about the right magnitude. The problem is the wrong phase. In other words, the prediction shown by the red curve did not match the data shown by the stars, which are a little bit hard for you to see. They have the different phase from each other. This is far from understood. Or those people who do understand it disagree strongly with the people who don't understand it. There are different definitions of vorticity that one can come up with. In some sense, some of them are ad hoc. It's not clear whether they're justified. This is some set of questions by Yuri Karpenko, which I think tells you that almost anything, we're not sure what is happening. His last one is error in the calculation, which, okay, that kind of shows where we are with this. This is a very important issue that we have to resolve. So even if I say it's well understood and calibrated to first order, it's still open. There's also experimental directions which have not really been explored completely. For example, if I have a system which, you know, has a vorticity direction that fluctuates event to event and within regions of the event, that's hard to measure. You, in fact, have to do spin-spin correlations. The idea being that whatever the vorticity is here where my marker is, I don't know what it is, but the neighbor of the lambda that's coming off does know what it is, and the spins will be aligned. This is an extremely challenging analysis. I don't know if it will ever be successfully done. I suspect that it will be done, and it will be a mistake because it's very easy to make a mistake in this one. Nevertheless, it's a future experimental direction. One of the most important, I guess, or equally weighted directions from experimental and theory is the splitting of the lambda and anti-lambda polarization. First of all, the question is, are the anti-lambdas shown in red here statistically higher than the lambdas shown in blue? Well, right now the answer is no. But you know, every data point sure wants to make you think so, huh? If they were higher, that could, for example, be evidence for a magnetic field, which is highly important to our field right now, because anti-lambdas have a different, opposite magnetic dipole moment than lambdas do. They'll pick up an extra polarization. So this could be an evidence of a magnetic field, but there are other explanations as well, if indeed there is a split. For example, we can have different freeze-out configurations. This is especially important at lower energies, where in fact the split might be growing. There could be core corona effects, which is basically also saying different freeze-out regions. And there can as well be hadronic effects. So this is another hot area of the field dealing with global polarization. I do want to say what's beyond global polarization and what are sort of the next frontiers that maybe aren't getting so much discussion right now. Well, first of all, what is getting discussed is very low root S, but usually in terms of global polarization. Let me talk a little bit about this. There's been a lot of work done on global polarization. On the right is shown global vorticity, which, as I said, is proportional to global polarization. And what we see, as we saw before, the vorticity or the polarization falls with energy, which at first might be surprising because the angular momentum grows with energy of a collision in a trivial way. But the point is the angular momentum density at mid-rapidity seems to fall with energy, and that's largely due to stopping phenomena. Stopping has a particular scale associated with it. There's a physical scale associated with it. And what a measurement as we go very low in energy might show is the competition between the increasing angular momentum that goes into a system as the energy of the collision increases, and the effect of stopping and transparency that leads to a reduction of the vorticity at mid-rapidity. The bottom plot reminds us that even if the vorticity at mid rapidity might be falling, the total vorticity, and hence the integral of the total polarization, is growing as a function of root S. That's why it's called total here. Okay, so that would be if I didn't just measure things at mid rapidity. And this is a nice work by Ivanov et al. This makes it very important. If we want to really understand this competition dynamics, we really do have to measure down to very low root S. At RIC right now, we can go down to 3, but we'd actually like to go lower, and Hades hopefully will have something to tell us at some point. 3 fluid hydrodynamics, as I said, this has a steady rise as we as the root S comes down, and we really would like to know, at least I would like to know, what happens if we lower it to threshold. We see that forward rapidity is important because that seems to be where the polarization goes, so to speak. There was a lot of work done on forward rapidity that I'd like to talk about now. There are a number of groups, Russian groups, that use a number of models, Cork-Lewin string model, hadron string dynamics, 3 fluid dynamics, all the rest of it, which suggest, or in fact demonstrate, that vorticity in these cases is largely confined to a layer between the spectators and participants. And again, that emphasizes the importance, especially at these energies where stopping is the major dynamic, of looking at mid rapidity and forward rapidity. Fortunately, at these energies, forward rapidity is not very far away. And one thing that has been seen are these vortex rings or vortex sheets. I've always found it funny that this one paper was calling them femtocyclones, which I thought was such a cool name, but I guess the PhysRev-C made the cyclones go away. But I always call it the cyclones. And so that's sort of a vorticity that goes around the beam axis. And I'll say a little bit more about that. Down here at the bottom, this just emphasizes the fact that even if I have a relatively narrow dn d-eta distribution, or dn dy, because I'm at such low energies, the vorticity itself can depend so strongly on rapidity, and that has to be measured. The interesting thing, if I take a look at this vortex femtocyclone and so forth, this is seen in all models, as a matter of fact, at these energies. Here's an example from a paper in 2015, rather early. And down at the bottom, we see a B equals 0 model. Okay, so the beam direction is looks like it's up down in this case. And what I find is, if I take a look at the vorticity, which is given by the color scale, here I have a negative vorticity, so I should curl my finger in, I guess. Here I have a positive vorticity, and then of course it extends out of the page. I have a ring of vorticity. Nothing's rotating. Okay, my vorticity points in over here, and then on the other side, and then it comes out over here and back around. A ring of vorticity in the forward direction, and an opposite ring of vorticity in the backward direction. A fascinating phenomenon. Most of the discussion in these papers have to do with the spatial characteristics of these rings, which is very interesting. And in as much as one's thinking about observable consequences, one says, well, what we really care about is a global polarization. And if I take, and that happens for non-central collision. So if I take a look at the top plot, this is for a non-central collision. If I have this sort of ring phenomenon and I have directed flow, which emphasizes this little lobe here, because I have positive directed flow at these energies, and this little lobe here, I will get an enhanced apparent global polarization, which is true, That's a little convoluted, and I must say, it kind of misses the point, the overall feature of the rings themselves, to focus on this small splitting. Another very nice paper came out just last year, actually, shows very clearly these vortex rings. This is now vorticity as a function of space, okay? But the spatial or the observational consequences were not so clear. Okay, so let's see, I'm gonna move a little faster. This is a simple, another paper, now a little higher energy, I think using 3 fluid hydrodynamics, if I remember. And here, the forward and backwards come apart relatively cleanly so that one actually ends up with a vortex ring. Once again, not a lot of discussion of finding the ring itself, mostly its effect on observable or apparent global polarization. However, because rings will expand, they do have radial flow after all, this ring itself should be observable. I can tell where this part of the ring went, and it had a vorticity pointing in a different direction than this point of the part of the ring. Once it's in momentum space, I can measure that. Okay, and in fact, this was realized by Xie et al. At very much higher energy. This is a calculation for RIC and also LHC. These are vortex arrows in coordinate space, X and Y, in the backward direction, this is gold, and in the forward direction. So we have counter-rotating, just like was seen over here by Ivanov, okay? But one thing that Xie did is point out that you can directly measure this ring. Don't worry about global polarization. And that's what's shown down here at the bottom. This then is the X component of the polarization shows a sine wave. The Y component shows a minus cosine wave, and this should be measurable, and it's on the order of 10% or so. Very strong. Not very different RIC to LHC. Okay. So seeing these rings, these structures which have never been seen before, would be fantastic. That would be really a compelling demonstration of fluid structure at places where it's not obvious. You can really treat it as a fluid in small details, and vorticity is small details of the fluid. So on the left, I showed these calculations, which I showed you before, 5 GeV. This ought to be observable at NICA, and I expect that you'll see this. But focus on measuring the rings themselves. The very interesting ring at 39 GeV, that would be accessible mostly at RIC. Unless we have a forward tracking upgrade, that will not be observed at RIC. If I take a look now at top energy RIC, and more importantly, the LHC, where the beam is clearly, the beam rapidity is clearly far away from any tracking detectors, at least in ALICE, CMS, and ATLAS. This would also not be an observed phenomenon because it's mostly forward focused at these high energies. However, LHCb should look for this. This is natural for them. They're already able to measure lead-lead collisions at the LHC. They have beautiful lambda reconstruction, particle identification, very nice tracking. They can find the polarization, and very importantly, you do not need an event plane for this sort of analysis. So these features are there, and they will see them if they just look. I'm pretty sure about that. Okay, I wanted to focus mostly on that. Hopefully, I reminded you that the hyperon polarization is a sensitive probe of the substructure, the dynamic substructure of the QGP that really convinces us that we can treat it as a fluid, and we understand it as a fluid. This is a new direction in a mature field. I mean, Peter reminds us how long this field has been in development and how far we've come. Polarization is just in the last few years that it's been experimentally accessible. There are important open questions, but I would say we're on good footing with lambda polarization. Maybe not so much with vector meson alignment. The energy dependence of the global polarization is very important, especially on the low side, where Nika and Fair can make contributions as well as RIC fixed target. We need to understand the forward, where the polarization is going as a function of rapidity, and that's good to have wide coverage at these low energies because we have competition between stopping and angular momentum growing. And in addition, besides just having global polarization, which is along the angular momentum direction, and longitudinal polarization, which is a small effect in the beam direction, there's a large effect, this ring-like structure. What I'm showing on the right-hand side, this can be for a B equals 0 collision. The angular momentum of this collision is 0. And furthermore, those little arrows, that's not even particles moving. Each one of those is a vortex. So it looks like a lot of rotation, a lot of structure here in a B equals 0 collision. These should be looked for and found. I think we'll be able to see them at low energy, and if LHC gets in the game, we should see them at the very highest energies. And I think we should make a real effort to pull these out because, you know, this is a new tool in our toolbox, but we're just at the beginning of learning how to use it. Okay, that's that.
Okay, Mike. Thank you very much for your great talk. I see a question from Jan. Yeah.
Yes. Okay. Can you hear me? Good. Hi, Mike. I have a question about I think slide 13 or 14, when you showed the comparison of the models with the data. And they were more or less, I mean, all of them more or less describe the data, even though they are based on very different descriptions of matter and different transport coefficients, let's say. So what is it what you really have to do to not describe the data? I mean,
yeah, you know, if everything describes the data, then you're out of luck. I think, you know, the main thing here is, and this is something that Yuri Karpenko found, is that you have to describe other features of the dynamics. For example, the sidewards flow, the V1, and not surprisingly, that's related to the angular momentum. Also, the dn data and the overall yields. I don't remember if each of these models, for example, chirokinetic, gets the dn data correct. But if you don't get the other features, you know, if you don't tune your model parameters to get, for example, dn data and V1, then you will miss the global polarization. So that's actually a good thing. It is sensitive to the tuning, but once you understand it based on other parameters, you find that you can understand the polarization itself.
Okay, thank you.
Yeah, any other questions? We have, yeah, Marco.
Hi, hello everyone. Hi, Mike. Very nice talk. I have a question at the kind of the very last slide where you emphasize this effect this ring effect that you can see for head-on collisions. That confused me a bit because I always think of this effects as related to the angular momentum of the whole system, or as you also discussed, or as of velocity gradients, which are, I think, somewhat related, although maybe so. Could you comment on how this is this then some kind of local effect?
Well, it's certainly local. It's certainly
and what
local.
sets the polarity? It's somehow inherited from where the beam comes from. Is that?
Yes, basically. Well, I mean, this is a gold-gold collision, so it's a symmetric collision. There's nothing special about the forward direction. Basically, if I'm taking a look in the forward direction, or I'm on the right-hand side, I have a gradient of velocities and temperatures, because you're usually looking at the thermal vorticity. I have a gradient of velocities and temperatures in the longitudinal direction and in the radial direction. And when I take a curl of that, that gives me the vorticity. At least that's the non-relativistic way to look at it. So yeah, it's really important. It is given by flow gradients or temperature and flow gradients, just like the longitudinal polarization, but it's not, you don't need any angular momentum to the system at all. That's true also for the longitudinal polarization. You know, you need a short axis and a long axis, but you can get that by colliding uranium atoms together, and you'll still have longitudinal polarization. So yes, it is surprising, and I'm glad you were surprised, because it is, it's remarkable. It's explained very nicely in this paper, and I've done a bunch of calculations with music. We see the same thing.